Hello, everyone. Today, we're diving deep into one of the most elegant and powerful mechanisms in modern operating systems, memory-mapped files, or mmap. Think about how programs usually interact with files. You open a file, seek to a position, read a chunk of data into a buffer, process it, maybe write it back out. It's a constant, explicit conversation between your application and the kernel. But what if you could treat a massive file on disk as if it were just a giant array in memory? That's the magic of mmap. It creates a silent, efficient bridge directly between your process's virtual address space and a file on disk. This technique is the secret sauce behind high-performance databases, log processors, and even language runtimes. But this magic comes with its own set of fascinating challenges. How does the system ensure that what one process sees in memory is consistent with what another sees? And when you change that memory, how and when does it actually get saved back to the disk? That's what we're here to explore, the critical concepts of coherence and dirty page writeback. So how does this mapping actually work? When you call mmap, the operating system doesn't immediately read the entire file into RAM. That would be incredibly inefficient for large files. Instead, it performs a bit of clever indirection. The kernel creates a mapping in your process's virtual address space. Think of this as reserving a range of addresses and telling the CPU, hey, if the program ever tries to access an address in this range, it corresponds to a specific part of this file on disk. The actual file data is loaded into physical memory on demand, one page at a time, through a process called demand paging. The first time you touch a memory address in that mapped region, the CPU triggers a page fault. The kernel intercepts this, finds the corresponding data block in the file on disk, loads it into a physical memory frame, updates the page table to point the virtual address to the new physical location, and then resumes your program as if nothing happened. From that point on, accessing that page is as fast as any other memory access. This lazy loading approach is the key to mmap's incredible efficiency. This on-demand loading is brilliant for one process, but what happens when multiple processes map the same file? This is where things get interesting, and it's where architects need to pay close attention. When you map a file with the map shared flag, you're telling the OS you want changes to be visible to all other processes mapping that same file. The kernel ensures this by having the page tables of all participating processes point to the same physical pages in RAM. A write from process A to a mapped memory page is instantly visible to process B because they are literally looking at the same piece of physical memory. The kernel's page cache acts as the single source of truth. Now, what about map private? This creates a copy on write mapping. Multiple processes can start by sharing the same physical pages for reading. But the moment one process tries to write to a page, the kernel transparently duplicates that page, gives the writing process its own private copy, and updates its page table. From that point on, its changes are isolated. This distinction is critical for designing robust systems. Are you building a high-performance IPC mechanism where processes need shared state? Use map shared. Are you loading a shared library where each process needs its own pristine, unchangeable view? Map private is your answer. We've seen how data gets into memory, but how does it get back to the disk? When your application writes to a memory-mapped region, it's just modifying a page in RAM. The CPU flags this page with a dirty bit in the page table entry. This is a signal to the kernel. This page's content in memory is newer than what's on disk. The write to disk doesn't happen immediately. That would defeat the entire performance benefit of mmap. Instead, the kernel uses background processes, often called writeback daemons or flusher threads, to handle this asynchronously. These kernel threads periodically scan for dirty pages. They gather them up and write them back to the underlying storage device in an optimized, sequential manner. This asynchronous writeback is a fundamental trade-off. It provides incredible write performance because your application isn't blocked waiting for slow disk I/O. However, it also means there's a window of time where modified data exists only in RAM. If the system crashes before the write-back occurs, that data is lost. For applications like databases that require durability, This is why they use mechanisms like msync to explicitly force the kernel to write specific dirty pages to disk, guaranteeing that a transaction is safely persisted.
So let's bring this all together. Why does understanding mmap coherence and writeback matter to you? For junior developers, when you use a tool like SQLite or an embedded database, you're likely using mmap under the hood. Understanding this helps you grasp why it's so fast and what its durability guarantees are. For mid-level engineers, this knowledge is key to performance optimization. When you're trying to reduce I/O bottlenecks, reaching for mmap can be a powerful tool, but you must be mindful of msync calls to balance performance with data safety. And for senior engineers and architects, this is fundamental to system design. Choosing mmap for inter-process communication or for handling massive data files is an architectural decision with profound implications for performance, complexity, and resilience. Understanding its consistency model allows you to design systems that are not only fast, but also correct. mmap isn't just a system call, it's a design pattern that trades simplicity for immense power, and knowing its inner workings is what separates a good engineer from a great one.